Okay, this is going to be chapter or unit 042 for oceanography, and we're still talking about that marine basin. We're going to talk about the continental margin, a little bit about the mid-ocean ridge today too, I think. But basically, we're going to start with the continental shelf. The continental shelf actually starts from the coast, from way up here, sorry, from the coast all the way to what's called the shelf break, which is right about there. And worldwide, that's all at about 135 meters. So we talk about quite a bit of water there, but in terms of the whole ocean, we're only talking 135 meters, so a little more than a tenth of a kilometer. And if you take a look at it, we're still talking about felsic rock. This is belonging to the continent, which is why it's called the continental shelf. And it actually has a very gentle slope. On average, it's around 3 degrees. And if you've ever seen a 3-degree tilt, we're talking about like parking lots where you park your cars going into a shopping center, and it's got a 3-degree tilt so we can get water off it. And that water, of course, also picks up the oil, which is less dense, and washes it into the storm drain and into the creeks, and all kinds of really bad stuff can happen with that. But that 3-degree tilt is what all we see on the continental shelf, and it gives it enough for the sediment that's coming off the continent to slide down with wave motion, actually wave motion at the surface, or actually wave motion in the actual vertical development of the ocean, and it actually takes that sediment and washes it down. It may be very narrow in case of an active continental margin, could be very wide compared to a passive. They can be anywhere from 20, 30 miles wide, maybe even 70, 80 miles wide, and they may be even less than, just a couple miles wide when we were talking about an extremely active continental margin. Average width of about 70 kilometers. Active margins are going to be more narrow, and passives are going to be wider. Continental slope is the next thing, and the continental slope actually is this section right here. So it's continental shelf to shelf break, and shelf break down to a depth of shelf break to deep ocean. So it actually goes all the way down to there. But it is the actual still the hard part of the continent. It does have the continental rise over the top of it, which is an accumulation of sediment. But now we're actually getting gradients relatively level to about 25 degrees. 25 degrees is about halfway to 45 degrees, which is basically halfway down. Average gradient of about 4 degrees. If you take a look at this, this is a vertically challenged, uh, vertically exaggerated continental margin. It doesn't look anything like this. This is more the scale, and I've enlarged it up here. So we have continental shelf to the continental break, and then this little section right there is the continental slope, and that section is the continental rise, and then we actually get to the deep ocean floor, the abyssal plain. So to scale, if you take a look at that distance right there, we're talking about 1,200 kilometers, and depth, we're talking about 5 to maybe 6 kilometers. So 6 kilometers is about right here. So we're basically exaggerating this thing, about probably 500 times, making it larger. But basically, and we'll maybe try this with the project we're going to do with sonar. Relief is greater at active margins than it is passive margins because of the continental shelf running into the deep ocean trench. Submarine canyons are located in the continental shelf. They go down the slope, and I'll show you a picture of those next. And they're caused by turbidity currents. And what a turbidity current is a mixture of water and soil. And you can get those when, like, the continental shelf gets too great, or there's an earthquake, or there's something that causes it to break down. You'll actually see this very viscous, meaning thick, fluid sediment accumulation that will actually go down and just kind of spread itself. And here's a model of one. And there's a YouTube video on the next page, which I probably will not show you. I'll maybe try to go to it really quickly. The continental margins can be modified by surface water. Rivers create submarine canyons. This is the Hudson River. We actually real close to New York City, and the Hudson River comes in, and it actually carries enough sediment that comes down and just like sandpaper gouges into the continental shelf. These are topographic lines, so as the lines get closer, the thing gets steeper and steeper, but they're also showing you that with the shading. but even on a flat map you can show that it actually is going downhill, but it's very gently sloped here until you get to this break, and then it slips down and then heads up on this continental rise, which is down here. But you can see the sediments that accumulate at the bottom of these canyons, and these are actually called submarine canyons. They're canyons underwater. Here's another picture a little closer to home, Chesapeake Bay. This is a submerged river valley. During the last ice age, this was actually a river, and since the ice melted and retreated off, and ice probably came down into Maryland, Virginia. But as the ice melted, it filled up, the ocean filled up, backwashed into the Chesapeake Bay, and now it's a submerged river valley along with all these other river valleys that are there. But sediments that come down here actually do come across the shelf, and they hit the slope, and they start scouring down with those turbidity currents. You have a Baltimore Canyon, a Washington Canyon, a Norfolk Canyon, and even have a Baccarat Canyon, or a landslide down here, which could actually start making a canyon if the landslide gets larger and larger. This is another picture of a turbidity current. This is not sure where this actually is located, but you can see these submarine canyons at the bottom are what are called lenses, sediment lenses of graded bedding. And if you actually look at this bedding, this was one turbidity current, there's another turbidity current, there's another turbidity current, there's probably another one down there, and there are more up top. So these are just layer after layer of sediment washing off the continental shelf, which scours the continental shelf. So let's go take a look at this one really quick, and I think I'm going to speed through it.
Turbidity currents are density-driven flows, usually at the bottom of the ocean.
So there is a turbidity current in a lab, and they're taking it with a slow-moving camera.
Body behind it,
watch this one.
and the very end of the tail. And from the other side, it looks very similar.
So that's
Once
a
again,
very
you can see the
dense
turbulent head, the
blob
body
of
behind
sediment
it,
and water
and the
going
very end
down,
of the
and you
tail.
can sort of see how that would
This
scour.
is a front view with the turbidity current running toward you. This was taken with a GoPro.
Okay, so that's a turbidity current, and you can actually type that in and see turbidity currents. And it's just graded bedding after graded bedding after graded bedding. Continental rise, which is this accumulated sediment that's down here in real slope. You can see it a little better here if we exaggerate it. It's a transition between the continental margin and the deep ocean, the abyssal plain. Sediments deposit here are waning turbidity currents, so as they lose energy, they eventually settle down in water. They get deposed or deposited, and they don't make it into the deep water, at least not the larger sediments. Not common on active margins, and again, that's because down here we have a trench, and this stuff actually gets pushed into the trench, or it gets built up into mountain ranges, depending on how much compression there is between the plates. Rise only exists where sediments can accumulate, and they only accumulate on flat, non-tectonically active floors. Deep ocean basin, usually it's underlain by oceanic crust, and ophiolite sequence, which we saw in that Earth Revealed series, where we actually have the sediments from the continent up at the top. We'll talk about pelagic sediment in the next unit, which we're talking about ocean sediments. We have pillow lavas underneath it, which actually say they were at the surface. We have what are called sheeted dikes. These things are vertically lineated basalts, and they have to happen underground. And then we have gabbro, which happens deeper in the ground, and we have peridotite, which happens deeper underground, and it's pretty much mantle type rock, but this is called an ophiolite deposit or ophiolite sequence. Seaward of and between opposite continental margins, so we have a continental margin on this side, so there's a continental shelf, a slope, a rise, and then here's the deep ocean basin, and we go all the way to the other side, and we can, if we have another passive margin like we do have on the east coast of the Atlantic or the west coast of Europe and Africa, goes back up to the rise, goes up to the slope, or the shelf slope, and then to the shelf, and then back over to the continent. Abyssal plains are very flat, and they're almost featureless. They're almost as flat as a tabletop. So here is the abyssal plain. There's the mid-ocean ridge, and we actually do have seamounts that are sitting up there. A seamount we'll talk about later, but basically it's an underwater volcano, has not reached the top. We do have these flat top ones also, which do say that they were at the surface, so they could have been up here and they were sticking up above as an island like this one or that one, and the waves erode the top, and as it gets closer and closer, the erosion basically stops and we get these tabletop or guyos. Fine-grained sediments are deposited or precipitated on the abyssal plain. We can get very thick sediments, but usually that sediment is farther away from the mid-ocean ridge because the rock gets older. We do have these normal faulting rocks on both sides, which show us the tension or the divergent. And we have volcanic seamounts. We have guyots, like these flat top things, and abyssal hills, which would be things that are usually lower than 1,000 meters high. Abyssal hills, and they cover large, vast areas of the deep ocean basin of the abyssal plain. Here's a picture of pillow lavas. These are fresh pillow lavas. You see there's very little sediment on them. And pillow lavas have to happen with basaltic molten rock hitting underwater cooling. And they actually cool and then get squirted out and cool and squirted out and cool and squirted out until the pressure's gone. These are sheeted dikes. This is actually Devil's Tower in Wyoming, but this was inside of a volcano when it got deposited, and the basalts that were coming in there actually solidified in these octagonal columns, which are called sheeted dikes. This is a hunk of gabbro, and you can start seeing a greenish color for olivine. This is peridotite with a heck of a lot more olivine, greenish color. And again, we have pelagic sediments. If this stays here for a while, it'll actually pick up sediments from the continents or precipitation from the things above. Then we have pillow lavas, and then we have sheeted dikes, and then we have gabbro and peridotite, and that's called an ophelitic deposit. Marine flood basalts, these are associated with divergent areas, and they can happen under the ocean, and they can also happen if we get on land masses where where the divergent happens. I grew up in Washington State and on the Colorado Plateau, and the Colorado Plateau is made out of flood basalts. Deep ocean trenches. Oceanic trenches are deep sea trenches. Most of these trenches are on the margin of the Pacific Ocean, the Ring of Fire. Deepest is the Marianas Trench, which is about 11,000 meters, which is about 7 miles deep. And relatively stagnant features, meaning that the deep ocean trench that sits right here stays right here, even though this plate may be moving this way and this plate may be moving this way. It's a relatively stagnant feature, and it's volcanic because we actually do get that rock to subduct down and it melts. It doesn't want to be down here. It punches up, and it's either an island arc where we get these islands on the ocean floor, or volcanic if we get an oceanic continental convergence. And then we also get what's called the Baccarat spreading center, and I'll show you that in a second. And that's always on the landward side of the volcanic arc. So here is that ophelitic deposit again. Here are the pillow lavas that actually happen with this molten rock squeezing out underneath the water. We have the sheeted dikes. I'm showing you the same type of rock, except it cools slower and gets this octagonal. And then we have gabbros, and if we go down deeper, we have peridotites, and it's pretty much coming from the asthenosphere down here. We can also see plate motion as these flood basalts come out of this relatively narrow hotspot. We can actually come up with a trail of volcanoes. The volcanoes become extinct, and so the volcanoes get older as they go that direction. So we can gain an idea of which way the plates are moving by these flood basalts or these volcanoes. The back arc, which you see right here, it's actually on the leeward side because the continent usually tends to be over here on the land side of the trench. We do have the islands which are located there, so we get this, and we get these volcanoes popping up on this side, and we can actually get a back arc, and we eventually could get a spreading center located right there, which is kind of cool. Not a real big concept in this class. But here's an example of the Marianas Trench, and it's going down, it's producing these volcanoes, which some of them are islands, and then back here we have this back arc spreading center, which is actually pushing this rock this direction, as well as this rock being pushed by the East Pacific rise, in this direction, so we actually do get them moving both ways, but this is a relatively stationary deep ocean trench caused by all this friction and breaking down of rock. Mid-ocean ridge, divergent area, looks like this with normal faulting going all over. We do get sediments. These things actually point north, sometimes they point south, showing us that if they formed at different times, we can see different amounts of sediment getting thicker both ways. So this is a divergent area. Here's another direction of it. You can imagine making these things, some of them point north, some of them pointing south. Here's another example I showed you with the pillow lava and the dikes and the gabbros and the peridotite, and those are the mid-ocean ridge, which is this 46,000 mile long spreading center. 75,000 kilometers, 46,000 miles, covers 23% of the Earth's surface, has a rift valley at the crest. It's a site of magma, pillow basalts, and ophiolitic sequences. We'd actually find the sheeted basalts down below, and we'd find the peridotite, gabbros, and the peridotite below that. We do have hydrothermal vents in some of these locations, and they can be white smokers, which is caused by beryllium, calcium, and silica. Or we can have, in warmer water, we can have black smokers. The animation looks a little off there, which is made of iron and sulfur. So warm water, black smokers, cooler water, it's because of the different samples. Warmer water, we get different things, like things with the highest melting points to solidify and form, and then cooler water, we get some of the different materials. Silicon, which actually makes up quartz, which is a relatively low melting point. These are pillow lavas, and we can get that when lava actually flows into the water, or it actually flows from under the water. These are pillow lavas sitting underwater. These are pillow lavas actually sitting above water, but we actually know that these formed underwater by the way they are. And another quick little look at a video. They're off the coast of Hawaii, and these are pillow lavas. And there are pillow lavas forming. And they do solidify very, very, very quickly. Nice water sound. There's a section where it's coming out of a very small opening, but I promise you that rock is still kind of warm. And here they are being squeezed out. You know, the shape of it actually gives rise to the word pillow. You wouldn't want to put your head on top of one of those because they are hard as rock. And you can see that they solidify and then they come squeezing out. It's almost like toothpaste out of a container. 4th of July, if you've ever played with those snake, those little pills you light and they produce these things, they remind me of those snakes, if they still make those, if you know what I'm talking about. But you just type in amazing underwater pillow lava and you can see this video as well. And it's got some really cool pictures of pillow lavas forming. Okay, I think we're getting really close. Here is the divergent area, and here's where we get that magma coming up when we get infiltration of water from the sea floor because of all the pressure, and the water goes in, it dissolves some of this material and comes out. Depending if it's hot water or cooler water, they're both going to be very hot. You're going to get either a black smoker if it's a hot temperature because it's pushing out mostly metals, solidifying. And then you can see we have sulfide deposits. And might as well take a quick look at this one too. You can see hydrothermal vents. That's actually a pretty good picture there. And so here comes the water out. It's got that black color because of iron, magnesium that are solidifying. It also has sulfur, which feeds bacteria, and the bacteria feed small little critters, and the small little critters feed bigger critters, sea worms, clams, shrimp. You can see there's the shrimp. More beautiful color shrimp, and I don't know why red's down there. Most of the things are white down here because there's no visible light, no advantage of having color, doesn't warn anybody or attract anybody. And then we don't know why these tube worms are actually red either. They do have a lot of iron in them, so it actually is sort of like the blood. Okay, black smokers, hotter water, iron and sulfur. White smokers, cooler water, calcium and silicon. Hot vent communities for chemosynthetic, it's sulfur, not sunlight. and they're bacteria that actually accumulate material because of the sulfur compounds that are in there. It uses sulfur other than sunlight and produces sugars. And we actually start the base of the food chain with the producers, and then we have consumers, all the way up to fish and crabs and other things. There really aren't a whole lot of large predators down here, unless they're occasional. Ocean ridge rifting, steeper, rugged, prominent rift zone due to that slow divergence. Ocean rise, so if we have a ridge, it usually shows slow divergence. If we have a rise, it's usually more gentle, it's less rugged, it's less well defined, and it's because of very fast divergence. The plates get moved apart very much quicker at a rise than they do in the ridge. Rises don't tend to be as high as the ridge. So here is an example of a mid-ocean ridge, and the plates moving in opposite directions. The divergence causing plates moving in opposite directions, sideswiping for the lateral faults, and then we have the fracture zones when the plates are actually moving the same direction, like they are there. So divergence, transform, fracture zones. And there's where we are going to stop. Actually, there's the fracture zone, which are aseismic, which means there's no seismic activity. They're scars. They used to be here, but they got moved over, and they're extensions of the transform faults that form. Okay, thank you much for stopping by. Appreciate it. 21 minutes. That's one of the longest ones yet.